All right, today we're diving into a huge topic in tech, system design. We're going to pull back the curtain and see exactly how engineers build the massive services that can handle, well, billions of us. Okay, if you were online back in the late 2000s, I bet this screen gives you flashbacks. Remember this guy? This was Twitter's infamous fail whale. It was basically a constant friendly reminder that even the biggest websites in the world can and do break under pressure. So it begs the question, right? Why do the biggest websites on the planet break? The services we use every single day, from social media to our banking apps, why do they just go down? Well, it's not just about the code. It's about something much bigger, the architecture holding all that code together. And that's where we get to the heart of it. The answer is system design. But here's the twist. It all starts with what feels like an impossible choice. A fundamental trade-off that every single system architect has to face. And spoiler alert, there's no perfect answer. So let's get right into it. So this impossible choice has a name. It's called the CAP theorem. And it's a really simple but powerful idea. It says that for any distributed system, and let's be real, that's pretty much any modern website or app you use, you can only ever guarantee 2 out of 3 super important things at the same time. Only 2. Okay, so what are the 3 things? First up, we've got consistency. Let's make this simple. Imagine you update your profile picture. With perfect consistency, the very second you hit save, every single person on Earth who looks at your profile sees that new picture. Instantly, no exceptions. It's like there's one single source of truth for everyone. Next on the list is availability. This one's pretty straightforward. This system is always on, no matter what. Every single time you make a request, say you pull down to refresh your feed, you get a response. The website is never, ever down, even if that response shows you data that's, a few seconds out of date. And the last one is partition tolerance. Now listen up, because this is the big one. This one is basically non-negotiable for any system on the internet. It just means the system has to keep chugging along even when parts of it can't talk to each other, because of network glitches. And since network failures happen all the time, you just have to be able to tolerate them. Okay, so here's where it all comes together. Since you have to have partition tolerance, that's a given, the real choice, that impossible choice, is between consistency and availability. You can't have both. Think about it. A bank absolutely needs consistency, right? When you move money, you need your balance to be 100% correct everywhere, instantly, even if that means the site is down for a second. That's a CP system. But for something like a social media feed, availability is way more important. You'd much rather see a post from 10 seconds ago than a big fat error message. That's an AP system. See the trade-off? That's the core dilemma. All right, so with that fundamental conflict in mind, consistency versus availability, what are the big picture goals that engineers are actually shooting for when they build these massive systems? Well, it really boils down to 3 main pillars. First up, and this is a big one, is scalability. It's a simple question. Can your system handle getting huge fast? I mean, what happens if your little app suddenly goes viral overnight? You go from 10,000 users to 10 million. Can your system handle that insane spike in traffic without just falling over and dying? That's scalability. And there are really 2 main ways you can do that. You can scale vertically, which is like swapping out the engine in your car for a much, much bigger one. You just make your one server more powerful. Or, and this is how most modern systems do it, you can scale horizontally. Instead of one supercar, you just add more cars to your fleet. You add more servers to share the work. It's almost always the better way to go for massive scale. The second pillar is reliability. Look, things are going to break. That's a fact of life. Reliability is all about building a system that expects failure and can handle it gracefully. The goal is to hunt down and eliminate any single point of failure, anything where if that one thing breaks, the whole show goes down. You want the system to just keep on running no matter what. So how reliable are we talking? Well, this number you see here is kind of the holy grail. It's called 5 nines availability. And what that means is, over an entire year, the system is down for a total of just over 5 minutes. That's it, 5 minutes of downtime in a whole year. That is an incredibly high bar to hit. And pillar number 3 is performance. It's dead simple. How fast is your system? The magic word here is latency. That's the tiny delay between you doing something, like clicking a button, and seeing the system respond. We've all felt bad latency. It's that frustrating lag. The lower the latency, the faster and happier your users are. It's that simple. Okay, so we've got our goals: scalability, reliability, performance. But how do engineers actually achieve them? What do they use? Well, they have a whole toolbox of proven designs and technologies. Let's crack it open and see what's inside. The first tool out of the box is the load balancer. And the traffic cop analogy is perfect. Imagine a flood of requests coming into your website. The load balancer stands at the front and intelligently directs all that traffic to a whole fleet of servers, making sure no single server gets swamped. This little component is absolutely essential for horizontal scaling. Next up, we have caching. You can think of this as your system's short-term memory. It's way, way faster than its long-term memory, which is the database. So for really common requests, like say a super popular celebrity's profile page, the system doesn't bother the slow database. It just keeps a copy in its super fast cache. This is one of the biggest weapons we have against latency. All right, now this one is a huge deal in modern system design, microservices. The old way was to build one giant, tangled application, a monolith. The new way is to break that huge app down into a bunch of small, independent services. The Lego block analogy is perfect. You have a block for payments, a block for user profiles, a block for search, and you can update, fix, or scale just one block without messing with any of the others. It's a total game changer. Of course, where you store all your data is critical, and there's a big choice to make here. On one hand, you have SQL databases. Think about them like a super organized spreadsheet. Everything has a strict structure, which is fantastic for consistency. On the other hand, you have NoSQL databases. These are more like a massive filing cabinet. They're way more flexible and are built to handle huge amounts of unstructured data and scale out horizontally. Again, it's another one of those big trade-offs. So you've got all these little Lego blocks, these microservices. How do they talk to each other? Well, you can do it synchronously. That's like a phone call. You ask for something, and you have to wait on the line until you get a direct answer. Or you can do it asynchronously. That's like sending a text. You fire off your message, then you can go do other stuff. You'll get a notification when the reply comes in. That asynchronous approach is absolutely key for building systems that are tough and flexible. So, we've got our big goals, and we've got our toolbox full of components. How does an architect actually combine all this stuff into a real plan, a blueprint? Well, it all comes down to designing at different levels of zoom, if you will. You always start with the high-level design. This is the 30,000-foot view, the overall architectural sketch. What are the major pieces of the puzzle, and how do they generally fit together? Once that's solid, you zoom in to the low-level design. This is the nitty-gritty blueprint for each individual piece. What does the code look like? How is the data structured? What are the exact rules for communication? You go from the forest to the trees. And this really brings us to the single most important idea I want you to walk away with. There is no such thing as a perfect system design. It just doesn't exist. Every single decision we've talked about, from that first impossible choice in the CAP theorem all the way down to your database, is a trade-off. Being a great designer isn't about being a magician who finds the perfect answer. It's about being a strategist who understands the compromises and makes the right trade-offs for the problem you're trying to solve. So, as we think about building the next generation of massive systems, the question we have to ask isn't, how can we build this perfectly? The real question is, what are we willing to sacrifice to serve the next billion users? It's a constant balancing act between consistency and availability, speed and cost, simplicity and features. It's about making those tough calls to build something that not only works, but works for everyone at a scale we can barely imagine.